So let's go back to solving quadratic equations. What causes the problem in the first place? It was something like this, where up until now we go, oh hang on, square root of negative 19, we can't get a solution, but now of course we can, because every surd with a negative number can be simplified. Because how do you simplify the surd? You want to rewrite it as the product of two things, one of those things being a perfect square. Well, negative 1 is now a perfect square. It's I squared. So this is minus 3 plus or minus the square root of 19i. Now be very careful. It's probably a better idea to write the I in front of the square root of 19. Otherwise it does look like I'm saying the square root of 19i. But the other nice thing now is that every quadratic can be done by completing the square now. Because every quadratic can be written as the difference of two squares. If I tried to do that with this one, you'd say, oh hang on, that's not the difference of two squares, but it is. Because I can rewrite that as minus 19 on 4 I squared. So everything now can be written as the difference of two squares. So I could say, oh well, it's x plus 3 on 2 plus the root 19 on 2i, x plus 3 on 2 minus square root 19 on 2i, therefore x of these two things. So creating quadratics, here's a nice thing. Every quadratic, it's also true for all polynomials by the way, but every quadratic with real coefficients, solutions will appear in conjugate pairs, and that's because when we solve it we go plus or minus the square root. So we must get the conjugates. So let's just expand that out and have a look. So what I'm saying is it can be factorised down to be x minus some complex number times x minus its conjugate. And if I expand that out, I get this, x squared minus z plus its conjugate x plus the multiplication of 2. If you add a number with its conjugate, then the imaginary part is going to cancel out. And you'll be left with twice the real part. And the last term there will be that sum of two squares. So if I now have to find this quadratic, there's the solutions. 4 plus I and 4 minus I can straight away go, well hang on a sec, the sum of the roots, I guess essentially is what we're saying, would be 8, twice the real part. Or you could just physically add them, I suppose. The product of the roots would be the sum of two squares, so 16 plus 1 is 17. So my quadratic equation must have been that. X squared minus 8x plus 17 equals 0. How do we find the square root of a complex number? Well, let's say the square root of our complex number is this other complex number, a plus ib. If I square both sides, I can create myself a nice little equation to go and find the values. Expand the left-hand side out, a squared plus 2abi minus b squared. The real part will equal the real part, and the imaginary part will equal the imaginary part. And again, simultaneous equations to go and solve. If I wanted to find the square root of minus 12 plus 16i, I can say, well, okay, a squared minus b squared would be negative 12, 2ab will be 16. I'll rearrange that to make b the subject, so it's 8 on a. Substitute into the other one, and I've got a quartic, but it's actually a quadratic because it's in that form where the powers are going down by an even amount. So it multiplies together to give negative 64, adds together to give 12, I get negative 4 and 16. So either a squared equals 4 or a squared equals negative 16. Now, I can reject this solution straight away. A squared can't equal negative 16 because a is representing the real part. Therefore, a squared has to be positive. My solution then is a equals plus or minus 2, which means b, and this is probably a bad way of writing it, because the way I've written it is sort of implying there's 4 solutions, because you could have plus 2 with plus 4, plus 2 with minus 4. No, I'm just basically saying the signs are staying the same here. Here's another difference though when we say the square root of complex number. If I was to say to you, hey, what's the square root of 16?
4.
Right, you only gave me one answer. You didn't say plus or minus 4, because the square root of 16 is 4. It's not minus 4. But because we can't order complex numbers, it's different. In this case, the square root does have plus or minus. There are some people that will say, oh, the positive square root is always when the real part is positive. So they would say the answer to this is 2 plus 4i. I'm not one of those people. I don't agree with that, because you can't order them. So who's to say? Why couldn't it be minus 2 plus 4i? Because imagine we got one where the answer was this. 2, let's just make it 2 minus 4i. And I'm saying, well, it's plus or minus. So my two possibilities is 2 minus 4i or minus 2 plus 4i. Well, what's so special about the real part? Why is the positive square root the one where the real part is positive? Well, why is that so special? Why can't the positive square root be when the imaginary part is positive? You know, they're just as good numbers, it's just a different set of numbers. So that's why we still go plus or minus. There's another way of doing it, which I think is a better way of doing it. I think it's easier. Same question. All right, remember we came up with this. A squared minus b squared is x, 2ab is y. If we play around with this a little bit, I think we come up with something neater. Have a look what I've done. I said, well, x squared plus y squared. If I was to actually work that out, look at what I get. I get a to the power of 4 plus 2a squared b squared plus b to the power of 4, which is a perfect square. It turns out to be a squared plus b squared squared. So now I can look at this instead and say, well, hang on, if I want to find the square root of x plus iy, then I can simply do this. A squared minus b squared is x, so that's still the same, that hasn't changed. But a squared plus b squared must be the square root of that sum of two squares that keeps cropping up all the time. That creates some very nice little simultaneous equations to solve. I can work out the a by simply adding the two together, or I could work out the b by subtracting the two. But as this thing, keep in mind though, how do you know then if it's plus or minus in that imaginary part? Well, you look at the value of the imaginary part. Now, if y is greater than 0, then a and b will have the same sign. If y is positive, a and b must have the same sign. They're both negative or they're both positive. But if y is less than 0, a and b must have had different signs. Minus 12 plus 16i. So same questions. How would I do it? I'd say, well, hang on. The difference of two squares is negative 12. The sum of two squares would be 20. This one's really nice because 12 and 16, and I'm sure you spotted it straight away, maybe, are two numbers of a Pythagorean triad. 12, 16, 20 is a Pythagorean triad. So a squared plus b squared is that third number, or the hypotenuse if you like, of the Pythagorean triad. Add them together, I come down to a being 2. I don't worry about plus or minus 2, because I know my final answer I'm going to go plus or minus anyway. So if a is 2, b is, well, imaginary part is positive, so it must have the same sign, so it's 4. Therefore my answer is, now I put the plus or minus in, plus or minus 2 plus 4i. I just think that's a heck of a lot quicker. This one, not a Pythagorean triad. Yes, there is a Pythagorean triad that involves 4 and 5, but unfortunately it's 3, 4, 5. You want the missing number to be the bigger number, and that's not what's missing in this one. There's not a Pythagorean triad that goes 4, 5 and a nice neat whole number. So what happens with this one then? Well, it now means a squared plus b squared will be the square root of 41. Can still be done with a little bit of patience. There we go. A is a half the square root of 10 plus 2 times the square root of 41. So now to work out b, I, inverted commas here, simply substitute back in. And there's b. Now, I have a look, I see, oh, the imaginary part is negative, so I know a and b will have a different sign. There is my square root. Plus or minus, I factorise the half out, but what a beautiful expression for the square root of 5 minus 4i. Now we're going to solve a quadratic where the coefficients are not real. They're not going to appear in conjugate pairs as solution now. Well, I could look at it and say, what multiplies together to give 2 minus 2i, and what adds together to give 2 plus i, and actually that one comes out quite nicely if you think about it. Probably though, most people will look at that and go straight to the formula. So let's do that, and you'll see when the answer comes out how it could have been quite nice by just going what adds together and what multiplies together. Substituting in, I've got to find the square root of minus 5 plus 12i. Beautiful. 5, 12, 13. Pythagorean triad, this one's going to be nice. Now let's just do it over here on the side. Difference of two squares will be -5. Sum of two squares will be that third number in the triad. 13. Add them together. I get A is 2. B is 3. Let me have a look at the imaginary part. The imaginary part is positive. So we get 2 plus 3i. Playing around with that, look at the two numbers. Okay, let's go back here. What adds together to give 2 plus I? What multiplies together to give 2 minus 2i? I and minus 2 minus 2i. If you spotted that, that could have been quick. But it's not something you necessarily do spot straight away with things like that. So we do tend to go to the quadratic formula. So let's now play.